Hey, good morning, guys. Assalamu alaikum. Welcome back to Physics Grade 12 by Inspired Teens, where in today's lesson we'll be continuing with work, energy, power. Okay, so last time I believe we ended on doing a question. Okay, so what we'll do is we'll continue with this question, but I just want to quickly revise the concepts that we discussed. Okay, so we discussed 4 different things. The first thing was work. Okay, so the work formula, the very basic work formula. Okay, work is measured in joules. So the formula that we worked with was W, which is work done on an object, okay, is equal to force, the force that's done on that object, okay, multiplied by the displacement. I see we didn't write anything for displacement. Multiplied by the displacement. Okay, this displacement is how far this object moves during its motion. Okay, multiplied by cosine theta. Okay, and this angle theta, we have 2 options for it. Okay, it's either 0 or it's 180 degrees, depending on which direction the object is moving. If the object is moving in the direction of motion, we use 0. If the object is moving opposite to the direction of motion, we use 180. Okay, and we said only parallel forces do work, perpendicular forces do not do work. That's why we said that for this force, okay, it's any parallel force that we can use, okay, any parallel force we can substitute into this formula to calculate the work that it does on an object, okay, and we can only substitute a parallel force into this formula. Okay, if there's a perpendicular force, we cannot substitute a perpendicular force to see what work a perpendicular force does, because a perpendicular force will never do work. Okay, so yes, let's move on to work energy theorem number 2. So this is the second formula that we learn. Again, the theorem definition, you will find that in your examination guidelines, but it follows this formula. It states that the net work done on an object is equal to the object's change in kinetic energy. Okay, and that's how this formula comes about. So we first have W net on the left-hand side, and W net can be broken up in one of 2 ways. Firstly, we can break it up utilizing this formula that we just learned. F net is equal to delta x times cos theta. So the force that we're using, since it's net force, the force that we'll be using is net force. Okay, that's basically how we get that. So F net times delta x times cosine theta. Or alternatively, we can actually substitute it using this algebraic sum of all the forces work done on that object. Okay, the work done by all the forces on that object, whatever it is. It could be applied, frictional, gravity, whatever it is, right? Then we have delta EK. Okay, and then delta EK is obviously half mv squared, EK final minus EK initial, and then we can simplify it to that. Then we get to 2 of the most important formulas, okay, which both fall under the energy principles. Okay, so keep that in mind. You need to know, if they say use work energy theorem, this is what they're talking about. If they use energy principles, this is what they're talking about. Okay, conservation of mechanical energy and non-conservative force. Those are the 2 different formulas for in the energy that can be found in energy principles. Okay, so let's have a look at conservation of mechanical energy. Conservation of mechanical energy states that the mechanical energy at point A is equal to the mechanical energy at point B. So mechanical energy is the sum of the potential, the sum of potential and kinetic. So EP plus EK at A is equal to EP plus EK at B. Okay, and we said there are certain conditions in order to use this formula. So in order for it to be in order to use this formula, the conservation of mechanical energy, there is only the conservation of mechanical energy only happens when we are in an isolated system. Okay, mechanical energy is only conserved when we are in an isolated system. So in order to use this formula, we need to be working with an isolated system. Now, in the question, what indicates to us that we have an isolated system? The fact that we have no friction, okay, no applied or no tension, none of those. Okay, the main one is no friction, but we also have to check no applied, no tension as well. Those should not exist as well. Okay, so remember I told you when there's no friction, this is the first formula that should come to mind. Okay, and please also check, make sure when you're checking for no friction, check that there's no applied and no tension as well. Okay, because when there's applied or when there's tension, then you cannot use this formula. Even if there's no friction, if there's an applied or a tension, you cannot use this formula. Okay, so just keep that in mind. Remember, this is the force formula that should come to mind in the absence of friction, applied, and tension. Then we move over to non-conservative force formula. Okay, and in the non-conservative force formula, it's WNC. So WNC is equal to delta EP plus delta EK. Okay, and now a non-conservative force, okay, includes all forces. Let's do this. A non-conservative force, okay, includes all forces except for Fg, or gravitational force, and Fg is the only conservative force that we work with. Okay, remember we defined non-conservative force as force, a force that is dependent on the force on an object that is dependent on the path that it takes, something to that effect. Okay, so if we consider Fg is conservative because it is not dependent on the path that it takes, because Fg is gravity, right? The Earth's gravity or any planet's gravity is going to pull an object down irrespective of what type of surface it's on. Okay, so yes, then we have this formula, WNC is equal to delta EP plus delta EK, and WNC, okay, so if you use that formula, do you say mg is equal to half mv squared? So, okay. No, actually. Okay, I'll answer your question when we go back to the question that we did. Okay, but no, you actually have to say mgh plus half mv squared for one point is equal to mgh plus half mv squared for another point. So you'll consider both for each point, but I'll show you an example in the question then when we continue the question. Okay, for those of you, a few of you have joined late, we're just revising the formulas, and then we're going to go back to our question. So yes, work done by the non-conservative force is equal to W, the work done by frictional force plus work done by applied. Okay, whatever force is non-conservative that we have, it could even be a tension. Okay. And we potentially could add Fg. Now I know what you're saying. Fg is not a non-conservative force, but remember, we could substitute it as 0. So it's no use adding it, right? If for some reason you added it in your algebraic sum, you would have to substitute 0, okay, because gravity is not a non-conservative force. Okay, so just keep that in mind. And then delta EP, okay, delta EP is equal to the change in potential energy. So remember, it's normally mgh final, the height at the final position, minus mgh initial. And how did we get this? We just took the common factor of mg. Okay, and here as well, it's half mv final squared minus half mv initial squared. And how did we get that? We just took the common factor of half m. Okay, again, that's common. Okay, and remember I told you can even, it's my favorite formula in the entire physics syllabus, because you can use it even with when you don't have any non-conservative forces. Even if you just have only conservative forces, you can still use WNC, which is amazing, right? Using WNC with no non-conservative force in the following way. So let's just say we have an example where the only force acting on an object is Fg. We are ignoring air friction. If an object is just falling in the sky, okay, and Fg is pulling it downwards, there's no other forces acting on it. You might think, okay, because we don't have any non-conservative forces, I cannot use WNC. And because there's no friction, I cannot use WNC. I should be using conservation of mechanical energy. Incorrect. You could use WNC. Okay, you could use WNC, but you just have to equate it to 0, because again, you have no non-conservative forces. So you could use this formula and just equate it to 0 and then calculate what you want to calculate, which is cool. Okay, constant speed, we said multiple things are true. Acceleration is 0, F net is 0, W net is 0, EK is 0. Keep that in mind. Existence of friction, I'm not going to go through that. That's very simple. This is just explaining what is a parallel force. So initially, we just had the orange force, right? We just had this orange force. Okay, and it was a diagonal force, 40 degrees upright. So the direction of motion is to the right of this object. This object is going to move to the right along this flat surface. So that force, F applied, is not exactly in the direction of motion, because direction of motion is to the right. Applied force is upright. They're not in the same direction. So its parallel component, that's what is going to do work. The parallel component of this applied force, the horizontal component, is what's going to do work. So we separate it into its component, and we understand that F applied parallel is actually in the direction of motion, or parallel to the direction of motion. Yeah, sorry, parallel to the direction of motion is better to say, because it doesn't have to be exactly in the direction of motion. If it's 180 degrees away opposing it, that's also fine. Okay. Okay, cool. Right. So now, okay. So remember also, I told you before we continue with this question, in a question, when they tell you, for example, use work energy theorem to solve the following questions. For your final exam, you are not limited to using what they tell you, okay? Because you will see in the memos have all the options. And if you use energy principles for a question that told you to use work energy theorem, then you will be marked correct, okay? For your class test, and that, check with your teacher how strict they are. They might want you to use what they ask you, what the question asks you to use, okay? Another thing is, if they do say use work energy theorem, please note that it is a hint that work energy theorem, the formula for work energy theorem, is definitely something you can use for that question, because this section, this topic, it gets confusing at times which formula to use. So if they say use work energy theorem and you are lost or you are confused which formula to use, then please use that as a hint to say, okay, since they're telling me to use it, I definitely will be able to use it. It doesn't mean you won't be able to use another formula. You might be able to use another formula as well. Maybe both formulas would work. But if they are telling you to use work energy theorem, then you definitely would be able to use work energy theorem. Okay. But yes, let's have a look at this question. The diagram below, not drawn to scale, shows a trolley of mass 38 kg released from rest at point A on an incline. ABC is a frictionless section. CD is a rough section, meaning it has friction, of the incline. The trolley reaches point B of the incline at a speed of 1.5 meters per second. Define the term non-conservative force. We said that a non-conservative force is a force acting on an object, okay, which the force, the work done on an object, a force acting on an object where the work done on an object is dependent on the path, okay, something like that. But the main thing is you need to know the work done on that object is dependent on the path. Just clarify the definition 100% with your examination guidelines. But the main thing, again, is the work done on it is dependent on the path. So example, like friction. Friction is definitely something, if you think of it logically, that type of force is dependent on the path. It's dependent on the type of surface that the object is flowing on. That's what it means. That's what the path means. Okay, and then conservative force, the only one we work with is Fg. And again, that doesn't matter. That just depends on gravity. Okay, so, and obviously mass of the object. Okay, yes, so we were going through this question. Okay, and we answered the first question. Point C is a point on the incline 0.75 meters lower than point B. Calculate the speed of the trolley when it reaches point C. So we walked from B to C, and since it was a frictionless section, B to C was smooth. That's why we took all the information in the paragraph and we put it into the diagram. Okay, and as you can see now, we have everything in our diagram. We can see that from A to B to C is smooth, and from C to D is rough. So from B to C, we actually figured that A was useless because they gave us the height of B, and then we needed to calculate the speed at C. So we only worked with those 2 points, right? And it was smooth. So remember, the first thing that should come to mind when you are dealing with a frictionless surface is conservation of mechanical energy. After that, you check, okay, is there no applied and there's no tension, and there's no friction, there's no applied, there's no tension. So we definitely will be able to use the conservation of mechanical energy. Okay. Also, another thing, a hint I told you is, okay, so for the person who asked about this formula, here we go. This is how we use it, right? So we answered 5.3. like this. Potential and kinetic at B is equal to potential and kinetic at C. Half mv squared plus mgh at B is equal to mgh plus half mv squared at C. Okay, so we have to get potential energy and kinetic energy at both points, the initial point and the final point. Okay, then we substituted values, and eventually we got an answer of 4,12 meters per second to the -1, and we put it into the diagram. Okay, another thing was, so another thing you can double check that you're using the correct formula is see what values you're working with. If you consider potential and kinetic energy, what parameters are they working with? What variables are they working with? We are working with height. Okay, mass and gravitational, that's normally given, right? Of course, we have height. Gravity is a constant. We're working with height and velocity. Right, height and velocity is the main things that you look out for. And yes, here in this from B to C, we're dealing with velocities and heights. Feel like, okay, cool. I have values that I can substitute into that formula. Then they said that the coefficient of kinetic friction between the trolley and the surface in section CD is 0.21. The trolley comes to rest at point D. So now we're dealing with CD. So the trolley has moved and we've gotten to C. And now, remember this final velocity for the motion from B to C, remember its initial velocity was 1,5, its final velocity was 4,12 at C. This final velocity is now going to become an initial velocity. It's now going to become an initial velocity for the motion of C to D. That just makes sense because it moves from C to D. Okay, just keep that in mind that we're dealing with a rough surface. Now remember the first equation when I told you, when you have a rough surface, when you have a frictional, when you have a question that has friction, okay, the first formula that should come to mind that you should think of trying is WNC. Okay, now again, I'm not telling you that WNC is going to work 100% of the time, but it's going to work a lot of the time, and you'll see as you practice more questions. Okay, so that's the first formula you should try, and if it doesn't work, then you can try another formula, perhaps work energy theorem. Okay, so yes, the coefficient. Okay, so they gave us the coefficient of kinetic friction. Calculate the magnitude of kinetic frictional force acting on the trolley as it moves from C to D. So this was a bit of Newton's. Okay, but frictional force is equal to normal force times mu k. Okay, frictional force we calculated. Sorry, normal force we calculated here. We remember that from Newton's. How do you calculate normal force? Up is equal to down. So, and then we drew the free body diagram, and then we realized the only up force is Fn and the only down force is Fg perpendicular. So equated them, we calculated Fg perpendicular, that gave us normal force. We substituted it into this equation, multiplied it by the mu k, and we got our answer for frictional force finally at 77,02. Okay, we all caught up. Use energy principles only to calculate height h. Okay, again, you're not limited to only using energy principles, but that's just for finals, I would say. Perhaps even for prelims, but more so for finals, I would say. How would you know if it doesn't work? How would you know if it doesn't work? Okay, that's a good question. Let's just say you have two variables that you need to solve for that are unknown. Maybe perhaps then it doesn't work. Okay, or you can substitute, have no variables, right? Remember, when you're solving for something, like for example, when I'm solving for this equation, I have to have something in my equation that's unknown. Otherwise, I'm not solving for anything then. Do you understand? I have to have something in my equation that's unknown. For example, here, this is my unknown. All the known values that I have, and then I have this one unknown. That just makes sense because now that's helping me calculate something. So if I have none of that, just I can substitute everything. This is 50, I have it. Then obviously that doesn't make sense, right? That's not going to work. Or if you have two variables, and in that case, you either need to calculate one of the variables or you're using the incorrect formula. Okay, but you will see most of the time this will work. Just practice questions and then you'll get the hang of it. Okay. So use energy principles to calculate height at h. Okay, so height at h is here. The height h. So it's basically the height of C that they want us to calculate. I'm going to get rid of this because we're done with it. Okay, they want us to calculate the height at C. So we actually have the velocity at C, and they told us that it comes to rest at point D, so we have the velocity at D as well. So heights and velocities again, and we know the height at D. The height at D is 0, okay, because that's touching the floor, or if we use relative height to C, we know they want us to calculate the height of C above D, so we can use D as 0. Either way, even if it wasn't on the floor. So energy principles, I'm going to use WNC to calculate the height at H. Now, WNC is work done by the non-conservative force. WNC is work done by the non-conservative force. Okay, so I want you guys to tell me what are or what is the non-conservative forces acting on the trolley from C to D? What are or is the non-conservative force or forces acting on the trolley from point C to D? Anyone? FA? Nope. There is no applied force acting on this trolley. Okay, let's read the question. The diagram below, not drawn to scale, shows a trolley of mass 38 kg released at rest. Released from rest at point A. It was just released from the top. There's nothing pulling it or pushing it. It's only using gravity to fall down this hill. Okay, so it's not applied. Friction is indeed correct. Okay, friction, we actually answered it yesterday in this one here. Friction. Okay, friction is the only force. Firstly, friction, yes, correct, friction. Friction is the only non-conservative force acting on the object. In fact, the only two forces acting on this object from C to D is friction and gravity. From A to B to C, it's only gravity. Okay, but from C to D, okay, it's friction and gravity. But remember that gravity is actually a conservative force. Okay, so we are using WNC, so we only consider non-conservative forces. Okay, so let's have a look. This is going to become work done by frictional force. This is equal to delta EP plus delta EK. So mg H final minus H initial plus half M. If these formulas confuse you, like taking the common factor, just let me know, then I'll use the full version. V final squared minus V initial squared. Okay, so work done by frictional force can further be opened up as the frictional force times delta X times cosine theta, right? That's work done by friction. That's how we calculate work done by friction, especially since we just calculated the value. That's why I'm opening it up, because we just calculated frictional force in the previous question, 77.02. So to calculate the work done by it, I can utilize this formula. Sorry, this formula here. It's equal to the mass of this object, I forget, is 38 kgs. This here is 9.8. Okay, let's consider what is the final height of this object from C to D. Remember, we're only working for the specific part of the motion from C to D. So the final height is at 0 because its final position is at D. Okay, so its final height is 0. So just keep that in mind. And its initial height is at C, which is actually what they want us to calculate. So I'm going to call it height initial. Or height at C, whatever. Half times 38 times final velocity minus initial. Final velocity is 0. Initial is 4.12. Perfect. Okay, let's substitute in here. Frictional force we calculated now is 77,02. Delta X, let's see if we have a displacement. Okay. So if we look here, we do not have a displacement. Okay. It's not given. The length of CD is not given. This delta X is not given. Okay. And if we use this formula, or if we look at our formula, all right, if I'm going to put in delta X, let's simplify. Okay, let's put delta X. Cosine theta is the direction that it's moving in. Is it opposing the direction of motion or is it exactly in the direction of motion? Frictional force always opposes direction of motion. So we're going to use cosine 180 is equal to, let's simplify these values. So I have 38 times 38 times 9,8. I'm going to multiply everything. It's going to become negative 372,4 times H initial plus, I believe that, I need to square these, I told you guys I always forget to square, so please remind me if I don't. This is also minus 300. When I simplify this, I'm getting 322,51. Okay, so now if we consider this left-hand side, here we have this. So remember, the question wants us to calculate the initial height, but now we have a second unknown. Okay, so remember I said when you have a second unknown, yes, correct, you only use 180 or 0 for cos. Yes, there's no need to analyze what's the angle between this and this. No, there's no need to consider any angle. You're either using 0 or 180. You use 0 when the object is moving in the direction of motion. Okay, and you use 180 when the object is moving opposite to the direction of motion. Okay, so remember I said, okay, if you have two variables, maybe perhaps you have used the wrong formula, but there's no need to just jump to another formula just as yet, because you'll notice when you use that other formula also, you'll end up with two unknowns. Okay, however, I'm going to teach you a concept that will avoid you from automatically trying to try a new formula. Okay, because you need to know this either way. Whenever you have a question, you need to know that you can express delta X differently, and it's very important. Okay, now let's consider, let's get rid of many of these things. We know it's rough. Okay, let's consider this triangle. You need to always remember this in a question. If there's a delta X unknown, or if anything, if the height is unknown, you need to know that you can use this triangle. It's a perpendicular Pythagoras triangle. So you can use trigonometric ratios to express certain values or to calculate certain values. Okay, so let's have a look, right? If I want to express, okay, the floor obviously I don't care about, right? The distance from here to here, that's like nothing really that I care about. So what do I care about? I care about what's opposite to 10 degrees, its height, and the hypotenuse, which is delta X. Okay, and that is sine. Opposite and hypotenuse uses the sine trigonometric ratio. So that's what I'm going to use. I can say that sine 10, okay, is equal to opposite over hypotenuse, H over delta X. And now delta X I can leave alone. You'll see why I would want to leave delta X alone. So delta X times sine 10 is equal to H. And then I can take sine 10 over as division. I get H over sine 10. So delta X can be expressed as, and you'll see it's not always in terms of unknowns, by the way. Like you'll see in some instances, you'll actually be able to calculate delta H or delta X utilizing this trigonometric manipulation, trigonometric ratios. Okay, so just always keep that in mind. You can always do this. You could even do it for the big triangle, for example, if we were working, if we knew this height, if we needed this height or the delta X or whatever it is. Okay, you could even do it for that because we have that angle. We always want to work with our opposite, which is our height, and then our hypotenuse, which is going to be delta X. This is like on an inclined surface, of course. All right, so please keep that in mind. So instead of writing, and by the way, this h is the h that we want to know. This is the h at C. Okay, the height at C. So I'm actually going to change this from initial to height at C. Sorry, just give me 1 second. Okay, so we want to change that. It's the same thing. I'm just showing you now. So now instead of delta x, I am going to express delta x as this. H, the height at C over sine 10. Now you'll notice in a few questions, you'll run into this issue where you don't know the delta x. Always remember this. Use trigonometry to manipulate it to try and express delta x in terms of h or whatever. Again, sometimes perhaps the height is known. Okay, and then you would be able to get a value for delta x. Okay, because you're dividing it by sine 10. So here, delta x, I'm going to be writing it as height at C divided by sine 10. 1 second. Okay, sorry about that. Sorry, just give me 30 seconds. Okay, sorry about that. I'm back. Okay, so now you see this delta x, instead of having it as delta x, we've expressed it as hc over sine 10. Okay, so now we have technically like two unknowns, but they're the same unknown. So this is perfectly fine. Okay, so I hope you're seeing how this is done. Okay, so again, don't rush to use a different formula just because this specific case we have two unknowns, because even in another formula, you're going to run into this issue where you don't have delta x. Okay, so that's the key to fixing that, is understanding this concept. Okay, that you can always use trigonometric ratios to express either delta x or h in some way, provided you have the angle or the delta x or whatever it is. Right? Sometimes they'll give you the height and they'll give you the delta x, and then they'll expect you to work out the angle. Okay, they won't explicitly tell you in a question work out the angle, but they'll tell you work out something else, perhaps the work done or the network. And in order to calculate that, you need the angle. And it's just implied that you need to know that you can utilize that trigonometric ratio thing to calculate that angle. Okay, so always keep that in mind. So this here is like it's like having a variable. So I'm going to rearrange this. It's like having 77,02 times 1 over sine 10 times hc. So I just moved hc to the side, times, it's not. Okay, and I can just move this to the end. Okay, so it's like I have a coefficient of hc. Okay, I hope that makes sense. Just to show it to you, like how you would calculate it. Alternatively, you could even just do that and then have it as a numerator and multiply both sides, whatever. So now I'm going to simplify this left side. It basically becomes 77,02 times cosine 180 times 1 over sine 10 And this gives me negative 443,54 times HC. I'm going to bring this HC over to the other side. It becomes plus 372,4 times HC is equal to, let's get this to the bottom. Let's get this over here. Okay, so it's basically like now I have a variable and then its coefficients, a variable and its coefficients. Okay, so that's why I'm bringing like the like terms onto one side. Okay, so let me simplify this. Negative 443.54 plus 372.4 actually gives you negative 71,14 times HC. Okay, and on the right hand side, of course, we still have this, which is negative 322,51. We divide both sides by 322,51. Of course, the negatives cancel out. We divide both sides by 71,14 actually. This cancels here. And we get HC finally as 4,53. Obviously, the algebra, I took many steps to solve the algebra. Okay, but like you can take however many steps you're comfortable with, provided you do not just don't make a mistake, right? However you're comfortable to solve your algebra, do it like that. Okay, you don't want to understand work energy power, go through all the hard work of understanding the tough concepts and the difficult questions to solve, and then make a mistake in algebra. Okay, so you want to be aware of that. Okay, so that's how we use work done by non-conservative force. I hope that makes sense. If you guys have any questions, please let me know. Okay, let's move on to the next question. In the meantime, though, let me just see which question should we be doing. Okay, let's have a look. Let's do this question here. Okay, an object moves up an inclined plane with an initial velocity of 5 meters per second. The magnitude of work done by the applied force is 1,500 joules. If the object experiences a frictional force of 40 newtons, find angle theta. Okay, so this is interesting, right? An object is moving up an inclined surface initially. They give us initial velocity, final velocity. They're giving us the magnitude of work done by an object. Okay, if the object experiences a frictional force of 40 newtons, find angle theta. Okay, so firstly, this entire motion has friction. So the first formula that comes to mind that I'm going to try is WNC. Okay, delta EP plus delta EK. By the way, you might see like delta U plus delta K, that's the same thing. Okay, the U is EP and then K is EK. Okay, so okay, actually, I'm gonna draw the bigger thing. So in this case, right, let's open up our formulas. So let's open up WNC. Now tell me, what are or is the non-conservative forces or force acting on this object? Tell me the non-conservative forces acting on this object. What are the non-conservative forces acting on this object? Okay, correct. One of them is frictional force, 100%. There's another one though. Okay, so definitely one is frictional force. That's a non-conservative force acting on this object during this motion. What's the second one? Correct. We have no, not Fg. Remember, we said Fg is a conservative force. Fg is not a non-conservative force. Fg is the only conservative force that we work with. So not Fg, right? Fa and Ff, correct, right? F applied 100%. F applied is the other non-conservative force that acts on object. It's anything besides Fg is a non-conservative force, by the way. Okay, so therefore this guy needs to be opened as work done by friction plus work done by the F applied is equal to mg height final minus height initial plus half m height v final squared minus v initial squared. So work done by frictional force. Okay, look at what we are given. We are given the value of the frictional force. So we know we can use that formula to calculate the work done by the frictional force. So I can further open this up as work done by frictional force times delta x times cosine theta plus work done by the applied force. Now, the work done by the applied force is given. So do I need to open this up? Do I need to open this up and say FA times delta x times cosine theta? No, I don't, because the answer to this is already given. If they gave me frictional force, maybe I'd open this up, but I don't have to because they give me the answer already. They tell me that the work done by the applied force is 1,500 joules. So this stays as is. This is work done by F applied because I have its value. Okay, and then of course we have the same thing here. Right, let us start substituting. Okay, work done by the frictional force is 40 newtons. It's given. Now delta x, let's see if we have delta x. And of course we don't. Is friction always a non-conservative force? Yes, most definitely. Friction is always a non-conservative force. Fg is not a non-conservative force. The only conservative force that you could potentially work with ever in the section is gravity. So any other force you can substitute into W and C. Applied, friction, tension, and whatever other force. Okay, got it. So friction, applied, tension is always going to be a non-conservative force. Fg is always not going to be a non-conservative force. Fg is always going to be a conservative force. Okay, so again, we don't know delta x, so we're going to use trigonometric ratios to represent this. So sine theta is equal to, I always use sine opposite and hypotenuse, right? Remember, it's an incline, perpendicular, blah, blah, blah. Opposite over hypotenuse. So opposite, the height is given as 5. Okay. And delta x is unknown. Right? So we substitute delta x there. Okay. So yes, indeed. So we can substitute delta x there. Okay, so just remember, okay, so here we could isolate delta x and sub it in. That would directly give us sine theta, but I'm not going to do that, and I'll show you exactly why. Because in this case, right, so remember they want us to calculate the value of theta. Okay, now you'll see why are we solving it. Okay, if I have to leave delta x as delta x, we will have every other value, so we can solve for delta x. Now, normally, remember, I told you, you sub this in if you don't know. You could do it. I'm just not doing it because I don't want to include sine theta into our calculations and make it complicated. So I'm going to calculate delta x and then sub delta x into this equation and then calculate theta. Okay, so let's do that. Cosine theta. Now remember, this theta is different. In the work formula, this theta is either 0 or 180. Since it's frictional force, it's always going to be 180. Cosine 180. And work done by the applied force, that was given as 1,500. Okay, there's no need to open this up into its work because the work done by the applied force was given. So I can substitute it there. Okay, mgh final minus mh initial. The mass of this object is given as 10. Okay, G is 9,8. Final height minus initial height. So in this case, it's moving from the bottom to the top. So the final height is 5. The initial height is 0. Plus half. M is 10. V final squared, that's 8 meters per second squared. Initial is 5 meters per second squared. So let's do that calculation. 8 squared minus 5 squared. Okay, so you see we have everything except for delta x. So when I simplify this right-hand side, 10 times 9,8 times 5 gives me 490. Okay. Half times 10 times the 8 squared minus 5 squared gives me 195. And on this side, when I simplify this, 40 times cos that, I get negative 40 delta x plus 1,500. Okay. And then I get negative 40 delta x. When I simplify the right-hand side and take over the 1,500, I get negative 815. This and this cancels. I divide both sides by 40. And I get delta x as 20,375 meters. Okay, it was 3 decimal places, so I didn't simplify it. Okay. Now, that's what I get, right? So now, this formula, WNC, gives you delta x, but they don't want delta x. They want theta, find the angle theta. But you see, this is why your understanding of this is where your understanding of this needs to come into play. You need to understand that how would you relate sine theta to delta x and h? Okay. Well, you ever come to a point where you can only use this formula, but you have two unknowns. So, okay, don't overthink it, right? Because majority of the times this formula is going to work. However, to answer your question, we did it in this case here. We had two unknowns, but it's not that we could only use this formula, but we used this formula and we had two unknowns. Okay, don't overthink it. Try different questions. Go and practice questions. Go and get a feel for questions yourself. Then you can answer those questions yourself to say, okay, did I ever come across a question where I can solve this? Or did I come across a question where I didn't know which formula to use? Could I use this formula? Did it have two unknowns? Okay, so don't overthink it beforehand and try to already eliminate and try to sort of see every single question what potential formula you can use. Okay, again, most of the time WNC is going to work. So like my advice to you is just to go and try the questions and you'll get a feel for how they ask the questions. Okay, and you'll get more comfortable with the formulas. Okay, so yes, in this case, WNC gets you delta x, but you need to understand that when you get delta x, that's how you're going to get sine theta. Okay, because sine theta is equal to 5 over delta x. You're using that trigonometry of this big triangle. And now all we need to do is simply substitute delta x. Okay, and then we shift sine it. So theta is equal to shift sine 20,375. Okay, and then when we do that, we get an answer of theta being equal to 14,21 degrees. Okay, I hope that makes sense. Now, I want to solve the same question using WNet. To show you that you don't have to always use the one formula, right? It is possible to use other formulas. So this is the first way. We're going to go a bit over time. Okay, just to solve this question quickly. So the first way and the second way. Okay, so the first way is using WNC. Again, I told you, whenever you have a question with friction, okay, your first instinct is to do what? It's to use WNC, and it's going to work majority of the time. When I mean majority of the time, I'm just being safe. It's going to really work most of the time. Okay, like try it out, like go do questions and you will see. Okay, so however, let's just say for some reason you would prefer using WNet. No problem. Let's try this question with WNet. So again, let's just read this question one more time. An object moves up an inclined plane with an initial velocity of 5 meters per second. The magnitude of work done by the applied force is 1,500 joules. If the object experiences a frictional force of 40 newtons, find angle theta. So W net. Now W net, when you are using W net, please keep in mind, you need to consider all the work done on this object. Remember, in WNC, we were skipping out FG, but in WNet, you cannot skip out FG. Okay, WNet is all the work that's done on this object. So even if you want, remember, the work done on an object comes from the force done on an object. So if you want, you could try and draw a free body diagram just so that you make sure you have all the forces that are acting parallel to the direction of motion. So we have FG, we have FN. So obviously FN is out, right? We have frictional force dragging it down and applied force dragging it up. Okay, so Fn is definitely not a force that does work because it's perpendicular to the direction of motion. Let's just consider the DOM, the direction of motion. Direction of motion is up the slope. So applied force parallel to direction of motion, frictional force parallel to the direction of motion, both of those. So both of those are going to be there. However, we need not forget the third one, and this is the key difference majority of the time between WNC and WNet, is the fact that you have to include FG. Now, we don't include FG because in its current form, okay, the way it's expressed currently, it is not parallel to the direction of motion. However, when we separate FG into its components, we have FG parallel, and we have, to forgive it not being 100%, like it's a bit skew and stuff. Let's just do this. Okay. And FG perpendicular. Now we notice, okay, let's get rid of that. Now we notice, okay, there is another formula which is parallel to the direction of motion, and we have to consider it. It does do work. 1, 2, 3. In WNC, we will not use FG because it's not a non-conservative force. However, in WNet, we will have to consider FG because WNet doesn't care about whether it's conservative or non-conservative. WNet just says the sum of all the work done on that object. And if there's 3 forces, you're going to have 3 work done on that object. So I'm going to have work done by the applied plus work done by the frictional force plus work done by FG, not just FG, okay? FG parallel. FG itself doesn't do work, okay? It's FG parallel. Okay, so the work done by, let's put an FA for uniformity. Cool. Okay, is equal to delta EK. So it's just equal to half M. Yeah, fine. It's equal to half M V final squared minus V initial squared. Okay, I hope you guys are with me. All right, tell me if you've lost me. So applied force, remember, the work done by the applied force was given as 1,500. So work done by applied force is 1,500. Work done by frictional force, okay, frictional force is given as 40 newtons. So I will need to open this guy up as FF times delta X times cosine theta. FF is 40. Delta X is the unknown we need to calculate. Cosine theta is cosine 180. Plus work done by FG. Right, now please pay careful attention to this. The work done by FG is calculated by using which force? FG parallel. Please do not use FG. Do not use FG perpendicular. You can remember the first thing we discussed in the section was the fact that you can only substitute a parallel force there. In this main work formula, the only force that you can substitute there is a force that's parallel to the direction of motion. You don't understand why we use Fn? Again, because Fn is not, let's consider the direction of motion. What is the direction of motion for this object, for this question? The direction of motion is up the slope. The reason we do not use Fn is because Fn is perpendicular to the direction of motion. In order to substitute a force into the work formula, into W net, in order to substitute a formula into W net, it needs to be parallel to the direction of motion. If it is not parallel to the direction of motion, it does not do work. Remember, we discussed it here. Work done on an object, and the force is any parallel force. And then if you look on the left, only parallel forces do work. Perpendicular forces do not do work. We cannot substitute it in. So in W net, this is only for parallel forces. And it's the same thing. It's the same thing for you. Only for parallel forces. Only for parallel forces. Okay. So yes, then we have FG parallel. So I'm going to calculate FG parallel. FG parallel is mg sine theta. Mg sine theta. So the mass is, what is the mass? 10 kg. 9,8. Sine theta. Remember, this theta is the angle of inclination, which is unknown. Okay, so you see this one is a bit more complicated because now we have two unknowns. Sine theta. Okay, times delta x, again, which is unknown. Okay, times cosine theta, which is cosine. FG parallel, also 180 because it's traveling in the opposite direction of motion. And equals to half times 10, okay, times 8 squared minus 5 squared. Okay, so if you'd like, right, you can continue this question on your own and solve it. However, I'll continue with this next week. Okay, so if you still don't understand something about Fn or whatever, just ask me next week and I will clarify it once more with you. Okay, but if you want, you can go ahead and solve this question on your own, but I will continue solving it next week and we'll do more practice questions for this section because it's needed. Okay, actually, we'll see how, depending on how the time goes, I think I might just finish this question and then probably start a new topic just because time is going. But yeah, okay, cool. Thank you guys so much for joining. Let's end it there. I will see you guys next week again, where I just discussed what we will be doing. But yeah, I'll see you guys next week. Ameen, Jazakallah khair, assalamu alaikum, and goodbye.